Okay, so we can now continue with our discussion regarding some typical transforms. We have started seeing the discrete cosine transform, and we said that the items of the transformation matrix can be obtained by using these cosine terms that we see on the screen, these terms, and when we apply them, what we come up will be the columns corresponding to these shapes, which are which can also be considered. The inverse of this will also give you just within a normalization factor the same shapes of the cosine shapes, and they will constitute the basis signals. And although it's not now in my notes, we have mentioned that the basis images in the two-dimensional case of a two-dimensional discrete cosine transform are outer products of these basis signals. Now, it may be a good idea to see what those basis signals and the basis images really look like once again, and then we will continue from there. So I'm switching the sharing to a web page, which is a Google search result with these terms, DCT basis signals. And it usually gives you, as you see on the left-hand side, the basis images. Mostly the basis images are given to you. But the basis signals corresponding to those in discrete time, at least, can be considered like the ones that you can see at the right-hand side. These are the one-dimensional basis functions or the basis signals. The first one is, as you see, the DC. The second one is a half sinusoid. The other one is a full cosine of one period only, and then 1.5 period, etc. It goes on and it increases up to something like a checkerboard, like frequency, or the smallest period that you can have, which is 1. And when you take the outer product of each of these things with another one, what you will get will be, since there are 8 such signals, 8 times 8 of these will produce the outer products. The outer product of the first one with itself will give you the DC at this corner that you see on the left-hand side, and one of the left-hand side images. And if you take the outer product of this one and the other one, which is next to that, it will give you this basis image. So in 2 dimensions, the basis images are obtained by taking the outer products. So that was what we have been talking about. And in continuous time, this may look like a good illustration over here. It's not the discrete time basis functions, but they look like they are continuous time versions, essentially. The others are just sampled versions of these basis functions that we can think of. All right, now I can switch back to my notes and we will continue from there regarding a few more issues of the discrete cosine transform. Let me wait while it switches. All right. Now, another thing that that is of interest in terms of the basis functions or the basis images, other than basis images and basis functions, is the implementation of the discrete cosine transform. And the implementation states that it corresponds to the discrete Fourier transform when you start from this signal. If you want to use the discrete Fourier transform, or if you want to find an analogy between the DFT and the DCT, what you have to do is you have to take a symmetric replica, you have to append a symmetric replica to that, and then make it a symmetric signal. And well, the symmetry is somehow problematic within a half period that we come up with here. Therefore, there is essentially some implementation further details. But if it is continuous time, if you can consider it to be continuous time, not the discrete, but the continuous cosine transform, let's say, what you will get will be a symmetric replica, which will make it a completely symmetric signal. And for completely symmetric signals, the Fourier transforms are real. So what we really do for the implementation is we take the DFT of this symmetric thing, which becomes real, and conjugate symmetric due to the essential property of the Fourier transform. But since there's no conjugation, since it's real, it is real and symmetric. So the DFT will also be, or the Fourier transform will also be real and symmetric, and half of it will correspond to the discrete cosine transform. That may be some sort of an implementation of the discrete cosine transform. However, I have to be honest about that. The discrete cosine transform implementation has faster operations than this because it's doubling the size first. Double the size and then apply fast Fourier transform. But since it's already double the size, it's not very efficient, but it's still more efficient than using this cosine transform with these items, with these elements as C, I, and M. But there are fast implementations, just like fast Fourier transform. There is fast cosine transform as well, which is not our concern for the time being. What is more towards our concern is once we see those things, is the two approaches that we have to understand, or the two significance of the discrete cosine transform. One of them is the discrete cosine transform essentially corresponds to the harmonic approximation of the Carhonen-Loewe transform, KLT, for a signal which is autoregressive 1, where the correlation coefficient rho approaches to 1. So if you have this kind of an autocorrelation matrix, and as rho approaches to 1, the corresponding KLT approaches to the discrete cosine transform. That's a significant thing. And it is very much commonly encountered in the nature, the autoregressive 1 sequences. Particularly most of the speech data, audio data, or images, even more than that, actually depend on this kind of an assumption of autoregressive 1. That's an approximation. But it is valid only for short distances, for short neighbors. For example, in audio signals, if you have, so let's say that this is an example. If you have a speech corresponding to saying merhaba in Turkish or in Arabic. So merhaba. It may look like this. Of course, I am just exaggerating the periods so that they become more eminent or visible. If you make a recording, probably the frequencies will not be as separate as this one. But when you zoom into that, you will start noticing the period. And if you zoom to, or if you focus to some milliseconds in this recording, audio recording, this signal around here will exhibit some low pass behavior, it doesn't have to be low pass, but it shows a stationary behavior. And in that stationary behavior, we can use, or we can approximate the signal to be essentially something like autoregressive 1. And with that autoregressive 1, you may try to design your transformation. You may want to design your quantizer. And accordingly, you may want to compress that segment. But if you look at the signal in another portion, like here, so these two will be different. So from the left to the right, from here to here, we cannot say that the same autoregressive AR1 stationary signal is proceeding. It's not actually proceeding. It changes characteristics. It changes the statistics. And since its statistics change, we cannot say that we can use the same transformation or the same quantizer setup. We have to change something. So in audio signal processing, although discrete cosine transform is not used, whatever transformation that you are using, you have to limit your transform or application into some smaller segments within where the stationary characteristics of AR1 process is continuing, or AR2 or AR10 essentially. Actually, for the speech compression, the model that they usually use is AR10. So that's why they use the linear predictive coding, not the transform coding, but the linear predictive coding that we have seen before in the format of LPC10, which means that we have 10 coefficients. I'm approximating 10 coefficients. And within this region, for example, I have 10 coefficients of CI, I from 1 to 10. But within here, I have this time DI from 1 to 10. Therefore, I'm representing with 10 coefficients in 1 millisecond and 10 coefficients within the next millisecond and 10 more coefficients within the next millisecond. Since I'm usually normally using more coefficients to represent 1 millisecond of audio, let's say 1000 coefficients, from 1000 to 10 coefficient conversion will become a compression. But it is segmented for some milliseconds of regions. Similarly, now we can proceed to the utilization of the discrete cosine transform, which is more into image compression. We will be using mostly, or in this well-known standards, they take the image. Let's assume grayscale image for the time being. For the color images, I will try to explain what they usually do. But for grayscale images, they split the image into 8 by 8 blocks. Okay, like this. So these are 8 by 8 blocks. And as you see, this block here, for instance, if it's the top left corner, it's usually, and if it's a landscape photo, for example, this place usually corresponds to the sky. And the sky here may be totally blue, whereas the sky here may contain some clouds. Therefore, the characteristics are different. So we have to consider the compression of this 8 by 8 block separately from this 8 by 8 block, or this one, or this one, mostly separately. And in the well-known compression method known as Jpeg, which uses the discrete cosine transform as the backbone of its compression methodology, they split the image into 8 by 8 blocks, and afterwards take this 8 by 8 block. It's not splitting anymore. I'm trying to show you the pixels here. It becomes an 8 pixel by 8 pixel image, quite a small one. And then it applies the DCT afterwards. And when you apply the DCT to such a small image, the assumption of autoregressive one usually holds very well. And since it works very well, the the most of the data that we can consider will be condensed this is the magnitude. Most of the data or the magnitude will be condensed into the first items, and the other items will become smaller, like this. So from this, let's say top left corner, I'm just trying to show it in three-dimensional kind of visualization. But what I really have is an equivalent of a high value, a large value, and some smaller values towards the other side. So at one corner, there's a lot of energy. That energy you can reimagine from our example that we have seen in previous weeks, where a 2x2 image was compressed and only the first item was large. All the other items were having small coefficients after the transformation. Okay, so in JPEG, we do DCT and the top left corner becomes large. And for the compression of this, some fancy things are done, like zigzag ordering. This ordering essentially makes the 8x8 two-dimensional discrete cosine transform output into a 1 times 64 one-dimensional signal, starting from the top left corner here and rendering in the zigzag order. The zigzag ordering is actually something like this. If I may illustrate, it's from here to here, and then from here to here, and then to the bottom, and then to here, and then to here, and then to the right, and then to here, and then to here, and then to here, and then to the bottom, here, 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 to the right. Okay, it's, as you see, a zigzag from the top left corner, kind of. If you think of it like a thread, you pull it from there, and then it becomes like a string. And that string has values which are usually in the form of a decreasing order, like this. Okay, they decrease. And then afterwards, we do, or before or afterwards, it doesn't really matter because it's the same data, it's just one-dimensional showing. We quantize. Essentially, we quantize before, afterwards, we make zigzag, but it doesn't really matter. So we get a quantized version of it. And we get something. And after that, after the quantization, we apply a lossless compression. So it can be Huffman coding, it can be arithmetic coding, whatever you may have. It's typically Huffman coding because arithmetic coding is copyrighted for most commercial purposes. But whatever, we have this lossless compression. Let's say it's something like a Huffman coding. And this Huffman coding is done for all the elements of xi, I from 2 to 64. That is all the coefficients except the first one. And for x1, what is typically done is to use a differential coding among blocks. So what I mean by this is the following. this one, for example, this block will generate a first value, which is the highest value, by the way. That high value is not encoded as it is. It's the difference between the highest value of this block, the highest DCT value that we generate from this block with the highest DCT value of the previous block. So we subtract it from that, and there's a differential difference between the DC values of the blocks. So it's like considering the whole image as a very low resolution image that you look from far away. And in that case, this will be 1 pixel of a low resolution, and this will be the next pixel of a low resolution image. And those low resolutions can be considered to have some kind of a relation among each other. There are block-wise similarities for neighboring blocks, at least. So we subtract the DC of this block from the DC of this block, and we encode them in a differential manner. In that way, what we avoid is the large values of the DC coefficients, which are significantly larger than all the other coefficients. So this shape that I have drawn is essentially quite inappropriate. It's not really correct. We usually have something like this, a very large first value, and the other values start from a lower value and proceed like that. The first DC value is usually very large. And because of that, they must have some differential encoding to reduce the size, the magnitude of that first element first, and then apply lossless compression. Otherwise, Huffman coding will go crazy because there will be too many symbols. As we know, Huffman coding works well if the number of different levels are finite, are not many. But if the DC is too high, they are usually distinct. So we will come up with a lot of large values, which is very bad for Huffman coding. So we try to avoid that using this differential coding of the DC elements only. All right, and there's one other thing. These are some technical details. If the rest of the values are too small, below a threshold or identically equal to 0, we put an end of block marker, and we don't try to encode the values with zeros. We just put an end of block. The rest is just 0. So the Huffman table will not include or pay attention to all these 0 values here and here and here and here. Although it may be very few bits, but there will still be some bits to encode these 0 values. You don't encode them. You just put an end of block marker. So as you see, the Jpeg is a very complicated compression standard. It is 1 by 1, taking into account what is happening to 8 by 8 blocks, and taking the DCT, quantizing, zigzag coding, Huffman coding, etc., and then writes some bits over there. Those bits are written to the file or transmitted, and then comes the next block. So if you try to look at the bits and see what's happening inside the JPEG file, you really will not be able to see the image. You have to really decode all those things and then obtain an 8 by 8 region and then patch it like a Lego block into the image. And then the next patch must be patched to the image. The next 8 by 8 must be patched. Once you patch everything into their correct coordinates, then you will have the image to be reconstructed. That's how JPEG essentially works. For color images, it's a very bad idea to apply the discrete cosine transform based method that I have just explained into the color channels individually, like the red, green, and blue channels. So we don't really apply the JPEG on red, green, and blue channels. Instead, we convert most of the things into let's say LAB or YUV channels. Let's say YUV channels. It's like one channel will contain the grayscale of the image, and the others will contain the colors and two color components essentially. One of them is HSV, you can say, for example. That is also possible. This is okay. This is okay. Let me continue from HSV because it makes more sense to explain everything. But for the others, it also works. For the YUV, Y channel is the gray level luminance kind of channel. In HSV, it is the V channel, value channel. In HSV, H corresponds to the hue, which means color, by the way. In, I don't know, in Greek or in Latin, I'm not sure about what's the origin of that word, but hue means color. S is the saturation of that color, how brightly saturated it is. And value is the intensity. It's not the saturation, but it's the gray level intensity. For example, a value of 0 will correspond to black, and a value of the maximum, which is, let's say, for 8 bits per channel, 255, that means white. So the highest value of any color will be white, and the darkest value of any color will be black. But whatever value you have in between, they will be there will be some hues and corresponding saturations. So we apply the JPEG into these three separate channels, which are uncorrelated within one another. We don't want correlation between the color channels. RGB, for example, they are essentially correlated. You may want to check out the RGB versions of some color images. Let us try to find some examples from the web. So I'm switching the sharing into my browser here, and let us see RGB channels. Let's see what kind of images will come out. Yeah, these are fine. For example, let's take a look at these. It's a cat image. It's blue, green, and red cat images that we have. And when you look at them, or maybe I have found a better image here, which is a parrot of RGB, red, green, and blue. Although the parrot contains seemingly no blue or green, when you take a look at the RGB channels as grayscale single intensity matrices, what you will see will be these three matrices. They look like grayscale, but the first grayscale matrix corresponds to the red channel, and the other corresponds to the green channel, and the last one corresponds to the blue channel. And as you see, the RGB channels both show the same parrot, which means that these three images are correlated with one another. And since they are correlated, individual JPEG applications to these three images will be very much redundant. We don't really want that because they have some cross correlations with one another. But instead of that, we have to convert everything into three color channels of, let's say, YUV. Let us try to see those channels. I want to show you this example. You see, these are the trees and things like that. The YUV channels, these three channels, although you can still recognize the trees and things like that somehow, they are not very much correlated to one another as strong as RGB. The correlations, the cross correlations are reduced. And one of the channels, which is the luminance channel, the value channel. Now let me go back to my notes again, and I will continue from there. What they do is they apply the they will, or we will be applying JPEG directly to this V channel or the Y channel of YUV. And the others, they show colors, color differences, we can say, because RGB here is multiplied by a 3x3 matrix, and what you obtain is, let's say, VSH, something like this. The other channels of the saturation and hue here, according to this, will have relatively smaller importance for the visualization. The first here, for example, for this matrix will be like 1/3, 1/3, 1/3. So V is like the average of RG and B. Okay, that is the average value. And human visual system is quite insensitive to colors. Of course, it's very much sensitive, but you can make this kind of a test by yourselves. In the dark, if I show you, relatively dark, if I show you two pieces of cloth, one of them is red and the other one is blue, and show them to you, you will not be able to see whether this one is red or the other one is red, which one is red, which one is blue. The color you will not be able to sense properly in the dark. And if I reduce this, if I downsample these H and S channels, they are images, as we know. If I downsample those images to a quarter, downsample by 4, like this, downsample them by 4. In fact, downsample them by 4 at all directions. So it's actually downsampling by 16. These smaller color differences, when they are upsampled further, they will still show you sufficient color information, and your eyes will not be able to differentiate. So we usually JPEG afterwards. These are the JPEG compressed data. How do we uncompress? We decode the JPEGs of each channel, and then we have to upsample by 4 and upsample by 4, and we have to combine them here for the image reconstruction. The original image will be reconstructed like this. By reconstruction, I mean if this is a color transformation, let's call it T matrix here, and this is the RGB vector, let's call it lowercase r, and this is the HSV vector, which we can denote as lowercase h. Lowercase h is capital T times r, therefore r is capital T inverse times h, right? So by this combination, I mean from these V, S, and H channels, V, S, and H channels, this combination corresponds to multiplying them with the inverse of this color transform and obtain RGB, because RGB is our original image. And when you show them, of course, this is a lossy compression. It's lossy from many ways. It's lossy because of these JPEGs here, and it's also lossy because of these color decimations. we downsample and we lose the information of colors, and afterwards we upsample them, so we insert zeros in between. But nevertheless, after this lossy operation, we come up with an image which very much resembles the original image. These downsampling strategies, you can take a look at their details from lots of web sources that are dedicated to JPEG. But yeah, for color images, this is what they do. A technical note, a further technical note to take a look at is the Q, which is essentially an 8x8 quantization matrix, where we essentially, let's say this is Q1, this is Q2, etc. We essentially divide every DCT coefficient, C, for example, C1, we divide it by Q1, and then we floor it. It's all rounded. We turn it into an integer. This is the quantization operation that is done. And these values of Q1, Q2, Q3, etc. Of course, C2 is divided by Q2 and then truncated. These operations become more and more significant, or they harshly quantize if these Q1s, Q2s, etc. are very large. So if these numbers are large here in your quantization table, so that's the name. If these numbers are large, then you quantize more. You divide by a larger number and then you truncate, which makes something very bad, because the values are have better tendency to get lost, or their resolutions become less and less. And as these Q values approach to 1, if they are smaller and approaching to 1, if all of them are 1s, for example, then it means you don't really do any quantization, because you divide by 1, that means you keep it. Of course, there is a quantization due to the truncation still, because the DCT values are real values, but nevertheless, it will be a better quality setting if these approach to 1. So let me put it like this. Qi approaching to 1 means better quality, and Qi increasing, of course, it's not tending to infinity. I'm just trying to say that it's increasing. It means better compression. And we all know that they are inversely proportional to one another. If you increase the quality, you have to reduce the compression ratio, because there is a fundamental concept of so-called rate distortion theory, and the distortion and rate are inversely related to one another. Okay, that is a fundamental theory, comes from the quantization concept. Rates and distortions are inversely proportional. So from now on, if you try to save your files using JPEG, please try to pay attention to the quality settings of those JPEG compressors. If they let you to choose some quality, they usually mention about some verbal things like excellent, high quality, fair, and low quality, and worse quality. Something like that, some 5 levels of slider. So excellent is something like these Q values become closer to 1. The fair, or the nominal quality setting, is the original quality setting that is proposed by the joint photographers experts groups, JPEG groups, and it's just some numbers. Those numbers, I don't have them in my mind, but you can always take a look at what these quantization table numbers are from the web. In fact, why don't we just try to search for them? It also helps us to understand how we can make research. It's not scientific research, but it's just some knowledge research from the web. Jpeg, sorry, quantization table. But yeah, I found it. These are the numbers that we divide. And they look pretty much random. I mean, they look very interestingly random. And it's the caption says surprises of JPEG quantization table. I'm not sure whether this is a good one. It may be quite deceiving, quantization table. So I don't really, yeah, let's look at the Wikipedia table. I think this is the correct one. The other one is quite incorrect because there are negatives and things like that. I'm sorry about that. This is more like it, the JPEG quantization table at its original default setting, or 75%, as they say. If you increase the quality setting from 75 to 80 or 85 or 90, etc., these numbers essentially become smaller and smaller. And they approach to 1. And if you reduce the quality setting from 75 to 70% or 65, 50, etc., then these numbers are multiplied, scaled by some positive numbers, some larger numbers, numbers larger than 1. Therefore, they become larger. And therefore, you divide by a larger number. Your DCT coefficient is divided by a larger number and then truncated, which will correspond to a case probably such as most of the items will become zeros. As you see, even these numbers are very large. 121 is quite a large number. In order for this coefficient, for example, to survive after the quantization, the value of the discrete cosine transform coefficient at this coordinate should better be larger than 121. If it is larger than that, when you divide it by 121 and truncate, it will be 1 at least, and it will survive. And in the reconstruction, it will be multiplied by 121. So you will see some harmonic of that coefficient in the image form. But if it is less than 121, it's gone. And if some of the items after the quantization are gone, we know that we apply an end of block marker. We deliberately put an end of block. So it's tending to divide these lower right coordinates, corner of this matrix, to larger numbers as compared to these numbers, which are relatively smaller. So DCT based JPEG tends to keep the lower frequency values in good fidelity, but they tend to harshly quantize the higher frequency coefficients. All right, so yeah, that's what it is. These are the quantization coefficients of the JPEG. I think we have seen a lot of JPEG, but for the last time, I want to see if there is any JPEG realization or JPEG algorithm. Oh, yeah. Okay, this one looks pretty good. Let's also see it like this. It shows a lot of detail. Some of these details are, yeah, I will skip and I will try to show you this visual. It makes better sense, I guess. It applies DCT and then the quantizer, as I remember, yeah, the quantizer was before the zigzag scanning, and then afterwards the entropy coder, and the entropy coder and the decoder shares the same Huffman table for the encoder and the decoder, because it's a standard compression. If you don't apply the standards of this standard compression, you have to submit or transmit the Huffman table that you are using to the receiver side, or you have to write it into the file as well. If you want to optimize your Huffman table for lossless compression, at each for each image, let's say, then you have to pay for it. You have to transfer the Huffman table. The quantization table is also predetermined. That is known in the encoder and the decoder. But it also depends on the quantization quality setting. So if you just write the quality setting, both the encoder and the decoder will know what kind of a quantization table it will use. I can see another interesting visual here, which converts the RGB into YCRCB, like YUV, and it splits them into 8x8 blocks, and to those 8x8 blocks, it applies the discrete cosine transform, quantization, zigzag coding, DC and AC separation. You remember that? Because DC corresponds to the first coefficient, and they are differentially coded. As you see, the DC is differential pulse code modulated coding, and AC has other compressions like run length encoding, Huffman or arithmetic coding, etc. And there's a start of frame for each 8x8 blocks. There's an end of frame or end of block, etc. And inside the between these two, you write the blocks one by one. All right. So there are a lot of nice visuals that are shown on the internet. For example, this one is a good one in the sense that I want to click on it and I want to enlarge it if I can. It's a demonstration. And interesting. It is okay. Let's take a look at the photo here. But whenever I show it with the cursor, it just spoils the image. It is, as you see from the image, cropping different 8x8 block positions, showing them separately. And when you take a look at the right-hand side of it, it shows first the pixel values of the corresponding 8x8 block. And below it, there is a DCT of it, discrete cosine transform of it. And the corner, as you see, is a large number as opposed to the other values, which are the AC, so-called AC coefficients, higher frequency coefficients, which are essentially smaller. And by after the quantization of that, they become even smaller. And the one-dimensionalized versions of those two-dimensional discrete cosine transforms are also shown. And here you also see the matrix format of what you have in the DCT. I liked it. Maybe I should bookmark it somehow so that yeah, I can show it from here. Maybe I can download to my desktop. And yeah, this is a preview, but anyway. Yeah, this is a good one. It makes way more sense. Demonstrations that Wolfram. So yeah, it's the Wolfram project, Jpeg compression algorithm. Yeah, I would truly recommend this for you to take a look at. Yeah. Okay, now let's go back to the sharing from my notes again. Essentially, we are finished with the discrete cosine transform, and let's give some break. After the break, we will do some very quick and short review of some other, unfortunately not so significant transforms, but they are very interesting. And they also help us to understand what kind of things can be done in compression. I will start mentioning about one transformation, one important transformation, which is not in the form of a matrix vector multiplication, but in the form of a sub-band decomposition. But it's also very much used in compression, so I have to mention about those. I will not go into the details of that. It deserves its own course of wavelets and sub-band coding. But we have to mention about those things very briefly. And today's lecture will be finished afterwards. And next week we will be proceeding to the coding efficiency issues of these things. How can we allocate bits to these things, which is also very much significant. And that will conclude all the things that we can see. If the subband coding will not be finished, it may not be finished today because of running out of time, we will continue next week with the wavelet transforms and subband coding. And afterwards, we will also see the bit allocation, which is utilization of transforms for compression, in other words. All right, now we can take a look at the, no, let's not take a look at anything. Let's give a break. Let's give a break until 11 o'clock. So at 11 o'clock sharp, let's meet here again and continue our discussion. But until then, let's stop the meeting for now. You may have some questions, but please do not ask them now. Let's wait until the end of the break. You may think of those questions and ask me afterwards, and I will give you the word over there. So let's end the meeting now, and let's see at 11 o'clock. Goodbye.
See you then.